When discover a new planet, the first question is always the same: how big is it? Out there, astronomers have found worlds far larger than Jupiter. Some are so swollen they're barely holding themselves together. Others sit right on the edge between planet and star, and every one of them is pushing against the same physical limits the universe refuses to break. Today, we're exploring the largest planets ever discovered, why none of them can last forever. Subscribe if you want to keep exploring the extremes of the universe. We all know Jupiter is 11 times wider than Earth. If you shrunk Earth down to the size of a grape, Jupiter would be a basketball sitting beside it. But the thing that surprises most people is this: Jupiter has no ground, no surface to stand on. The entire planet is atmosphere, gas piled on top of gas, compressing tighter and tighter. As you sink until deep inside it becomes something stranger: liquid, metallic, hydrogen, maybe a rocky core, the size of Earth buried at the center. Nobody's completely sure. The planet spins once every 10 hours. That's the fastest rotation of any planet in the solar system. So fast that the whole thing bulges outward at the equator and flattens at the poles like wet clay on a spinning wheel. And despite being only 11 times wider than Earth, Jupiter is 318 times heavier. It contains 71% of all the mass in every planet orbiting the Sunday. If you melted down Saturn, Uranus, Neptune, Earth, Venus, Mars, and Mercury, and combined them into one ball, Jupiter would still be heavier. But here's the paradox. For all that weight, Jupiter isn't dense. It's made almost entirely of hydrogen and helium, the two lightest elements that exist. The overall density is just slightly more than water. You could theoretically float a chunk of Jupiter if you had a bathtub big enough, though it would sink slowly because it's still denser than pure hydrogen gas. Galileo Galilei first spotted Jupiter's 4 largest moons in 1610 through a handmade telescope no better than a pair of modern binoculars. Those moons, Io, Europa, Ganymede, and Callisto, orbit Jupiter, just like a miniature solar system, and their discovery shattered the ancient belief that everything in the cosmos revolved around Earth. If moons could orbit Jupiter, then maybe Earth wasn't the center of everything. Centuries later, we sent spacecraft. Pioneer 10 flew past Jupiter in 1973, the first human-made object to visit the outer solar system. Voyager 1 and 2 followed in 1979, sending back the first detailed images of Jupiter's swirling cloud bands and the Great Red Spot, a storm larger than Earth that's been raging for at least 300 years, possibly much longer. Then came Galileo, which orbited Jupiter for 8 years starting in 1995, dropping a probe into the atmosphere that transmitted data for 57 minutes before being crushed by the pressure. The Juno mission, which arrived in 2016 and is still operating, has rewritten what we know about Jupiter's interior. The spacecraft's instruments detected that the core isn't a neat, solid ball of rock and metal like scientists expected. It's fuzzy, diluted. The heavy elements seem to be mixed with the surrounding hydrogen, creating a gradient rather than a sharp boundary. Some researchers think a massive impact early in Jupiter's history, possibly a collision with a planet-sized object, 10 times the mass of Earth, shattered the original core and scattered it throughout the interior. The evidence is still being debated, but it suggests Jupiter's history was more violent than the calm giant we see today. Saturn, meanwhile, pushes the paradox even further. Saturn is 9.5 times wider than Earth, almost as big as Jupiter, but it weighs only 1/3 as much. Same ingredients, mostly hydrogen and helium, but less compressed. The density drops to less than water. If you could build an ocean large enough, some absurd bathtub stretching 200,000 kilometers across Saturn would float. A planet, nearly the size of Jupiter, bobbing on the surface, like a beach ball. This wasn't always obvious. When Galileo first observed Saturn through his telescope in 1610, he saw what looked like 3 objects, a central disk with 2 smaller companions on either side. His telescope wasn't strong enough to resolve the rings, so he thought Saturn had ears or was a triple planet. It wasn't until 1655 that Dutch astronomer Christiaan Huygens, using a better telescope, correctly identified the features as a ring system encircling the planet. The rings are stunning, but they're also fragile. They're made of billions of chunks of ice and rock, ranging in size from grains of sand to house-sized boulders, all orbiting Saturn in a thin disk. The entire ring system is about 280,000 kilometers wide, but only 10 to 100 meters thick in most places. If you scaled the rings down to the size of a football field, they'd be thinner than a sheet of paper. And they're disappearing. Observations from the Cassini spacecraft, which orbited Saturn from 2004 to 2017, revealed that the rings are raining down onto the planet. Charged ice particles are pulled along Saturn's magnetic field lines and dumped into the upper atmosphere at a rate of around 10,000 kilograms per second. At that rate, the rings could be gone in less than 100 million years, a blink of an eye in cosmic terms. Cassini's final act was to dive into Saturn's atmosphere in September 2017, transmitting data until the very end. The mission discovered that Saturn's magnetic field is almost perfectly aligned with its rotation axis, which is bizarre. Every other planet has a tilted magnetic field. Scientists still don't know why Saturn is different. Both Jupiter and Saturn formed about 4.5 billion years ago, when the solar system was just a disk of gas and dust swirling around a young sunday. Jupiter condensed first in the region beyond the frost line, the distance where temperatures were cold enough for water, ice, and other volatiles to freeze. This gave Jupiter access to a huge reservoir of material. Once its core reached about 10 Earth masses, it triggered runaway gas accretion, pulling in hydrogen and helium from the surrounding disk faster and faster, until it became the giant we see today. Saturn formed slightly later and slightly farther out, where the disk was thinner and less dense. It didn't capture as much gas, which is why it's lighter. Some models suggest Saturn tried to migrate inward toward the Sun early on, but Jupiter's gravity blocked it, locking both planets into a gravitational resonance that kept them stable. This is called the Grand Tack hypothesis, and it might explain why the inner solar system is relatively small and rocky, while the outer system is dominated by gas giants. Jupiter and Saturn are stable. They're not being scorched by the Sunday. They're not losing atmosphere. They've been in roughly the same orbits for billions of years, and will stay there for billions more. When astronomers talk about planets around other stars, Jupiter and Saturn are the measuring stick. Every new discovery gets compared to them, twice the size of Jupiter, half the mass of Saturn. These two define what normal looks like, which is why the planets we've discovered outside the solar system are so unsettling. Some are twice Jupiter's size, but way less than Saturn. Some are smaller, but 9 times heavier. Some orbit so close to their stars that their atmospheres are boiling off into space, inflated to sizes that shouldn't be physically possible. These aren't stable worlds quietly orbiting for eons. They're extreme, violent, and temporary. The largest of these, the widest planet we've ever found, is so bloated and so light that it defies every model we had. It's a soap bubble in a furnace, and it's barely holding on. HAT P67b is the widest planet ever discovered. It's just over twice the radius of Jupiter. If Jupiter is a basketball, HAT P67b is a yoga ball sitting next to it. But here's what doesn't make sense: it weighs only 1/3 as much as Jupiter. For a planet twice the size, you'd expect it to be heavier. Instead, it's lighter, much lighter. The density is absurdly low, less than styrofoam, less than cork. Closer to the density of aerogel, that strange solid material that looks like frozen smoke and is mostly empty space. A planet the size of 2 Jupiters, and it weighs almost nothing. When the discovery was announced in 2017 by the Hungarian Automated Telescope Network, some astronomers initially thought there was a measurement error. Planets weren't supposed to be this puffy, but the numbers held up. Follow-up observations confirmed it. HAT P67b is real, and it's one of a strange class of worlds called super-puffed planets, or cotton candy planets, gas giants that have inflated to enormous sizes because of where they orbit. HAT P67b circles its star once every 4.8 days. That's not a typo. 1 year on this planet lasts less than a week. The distance between the planet and its star is only 6.5 million kilometers. For comparison, Earth is 150 million kilometers. From the Sunday, Mercury, the closest planet in our solar system, orbits at 58 million kilometers. HAT P67b is 9 times closer than Mercury. It's skimming the outer edge of its star's atmosphere. At that distance, the radiation is brutal. The star is a Type F star, hotter and more luminous than the Sun, and it's blasting the planet with high-energy photons around the clock. The temperature on the day side climbs to around 2000 degrees Celsius. Hot enough to melt aluminum, hot enough to vaporize rock, and all that heat does something strange to the hydrogen and helium that make up the planet. It heats them so much that they expand outward like air inside a balloon held over a flame. But there's another piece to the puzzle. HAT P67b doesn't weigh much, so its gravity is weak. Gravity is what holds a planet together, pulling the atmosphere inward. If gravity is weak, the atmosphere can drift outward, ballooning into space with very little resistance. The result is a planet that looks enormous but feels like nothing, a cloud pretending to be a world. Heather Knutson, a planetary scientist at Caltech who has studied super-puffed planets extensively, described them as existing in a delicate balance. The heat is trying to blow the planet apart. Gravity is trying to hold it together. And for a brief window of time, cosmically speaking, the two forces are almost equal, allowing the planet to inflate to these absurd sizes. But it's not stable. The balance won't last. TRES 4b, discovered in 2007, was one of the first super-puffed planets astronomers found. It's almost twice the radius of Jupiter, but weighs slightly less. The density is about a third the density of water, lighter than most types of wood. When the Discovery team first published the findings, some scientists were skeptical. The prevailing models of planet formation didn't predict anything like this. Planets were supposed to be dense, compact objects. TRES 4b looked like a mistake, but more planets like it kept turning up. WASP 79b, WASP 17b, Kepler 51b, which is even puffier than HAT P67b in some measurements. Each discovery reinforced the pattern. These planets are rare, only about 5 to 10% of hot Jupiters are super-puffed, but they're real. The leading theory for why they exist involves a process called ohmic dissipation. The idea is that the planet's magnetic field interacts with the ionized gas in the upper atmosphere, creating electrical currents. Those currents generate heat through resistance, similar to how an electric stove burner heats up. That extra internal heating, combined with the external heating from the star, inflates the atmosphere even more than radiation alone could explain. Joshua Wynne, an astronomer at Princeton, has argued that ohmic heating might be the missing ingredient that explains the most extreme super-puffed planets. But not everyone agrees. Some researchers think tidal heating plays a bigger role. If the planet's orbit is slightly elliptical rather than perfectly circular, the star's gravity squeezes the planet more during the close approach and less during the far part of the orbit. That constant flexing generates heat through friction, like bending a paperclip back and forth until it gets warm. The heat inflates the planet. Eric Lopez at NASA Goddard has modeled this process and found it could account for some of the puffiness, though probably not all of it. Another idea involves the planet's composition. Most gas giants have a core made of rock and ice, surrounded by a thick envelope of hydrogen and helium. But if the core is unusually small, or if the planet formed in a region of the protoplanetary disk that was depleted in heavy elements, then the planet could be almost pure hydrogen and helium with very little else. Pure hydrogen is the lightest possible material. A planet made mostly of it heated to extreme temperatures would naturally puff up more than a planet with a heavier core. Whatever the cause, super-puffed planets don't last. The same heat that inflates them is also stripping their atmospheres away. High-energy photons from the star hit the upper atmosphere and knock gas molecules loose, sending them flying off into space. HAT P67b is losing around 10 million kilograms of atmosphere every second. That sounds catastrophic, but the planet is so massive that it would take hundreds of millions of years to lose a significant fraction of its mass. Still, it's happening. HAT P67b is evaporating, slowly, steadily bleeding gas into the void. Eventually, maybe in 500 million years, maybe in a billion, the outer layers will thin. Or maybe the core will be exposed, a rocky remnant stripped of its atmosphere entirely. Astronomers have tried to find super-puffed planets around older stars to see what happens in the long term, but they're extremely rare. Most of the super-puffed planets we've found orbit young stars, less than a few billion years old. The older the star, the less likely it is to have a super-puffed planet. The implication is clear. These planets are temporary. They inflate, they evaporate, and they disappear. But if you think 2000 degrees is extreme, there's a planet out there that makes HAT P67b look cool by comparison. A world so hot that the very chemistry of its atmosphere breaks down and the sky glows like molten metal. Kelt 9b is the hottest planet ever discovered. The dayside temperature reaches 4,600 degrees Kelvin. In Celsius, that's 4,300 degrees. Hot enough to melt titanium. Hot enough to vaporize iron. Hotter than many stars. The planet orbits a star called Kelt 9, which is itself one of the hottest stars known to host a planet. Kelt 9 is a Type A star, a category of stars that burn at temperatures around 10,000 degrees at their surface, nearly twice as hot as the Sunday. And Kelt 9b is so close to this star that it completes one full orbit every 36 hours. A year on this planet lasts a day and a half. The distance between the planet and the star is just 6.4 million kilometers. That's less than 5% of the distance between Earth and the Sunday. It's close enough that the star's gravity is distorting the shape of the planet, pulling it into an elongated egg shape. Close enough that the star's radiation is literally tearing the atmosphere apart. The discovery was announced in 2017 by the Kelt Survey Kilodegree Extremely Little Telescope, a network of small robotic telescopes designed to find transiting planets. When the first measurements came in, the science team was stunned. They'd found hot Jupiters before, but nothing like this. The temperature was so extreme that it broke all the existing atmospheric models. Kelt 9b is tidally locked, meaning it always shows the same face to its star, just like the moon always shows the same face to Earth. One side is permanently scorched by starlight, the other side is in eternal darkness. But even the night side stays absurdly hot, around 2,500 degrees Celsius, because the atmosphere is constantly churning. Winds race from the day side to the night side at speeds over 5,000 kilometers per hour, trying to equalize the temperature. They never quite succeed. The temperature difference between day and night is still around 2,000 degrees. At 4,600 degrees, something fundamental happens to matter. Normally, gas in a planet's atmosphere exists as molecules. 2 hydrogen atoms bonded together. 2 oxygen atoms bonded to 1 hydrogen to make water vapor. Carbon and oxygen bonded into carbon dioxide. But at 4,600 degrees, the thermal energy is so high that molecular bonds can't survive. They snap. Molecules are ripped apart into individual atoms flying around on their own. Kelt 9b's atmosphere doesn't have water molecules. It doesn't have hydrogen molecules. It has loose hydrogen atoms, loose oxygen atoms, loose iron atoms. Spectroscopic observations conducted using ground-based telescopes and the Hubble Space Telescope have detected gaseous, iron gaseous, titanium gaseous, sodium gaseous, magnesium, all of them floating around as single atoms not bound into compounds. Kevin Heng, an astrophysicist at the University of Bern, who has modeled Kelt 9b's atmosphere, described it as being more like the atmosphere of a star than a planet. The conditions are so extreme that normal planetary physics doesn't quite apply anymore. You have to start thinking about plasma physics, ionization, and radiation pressure forces that are usually only relevant for stars. The iron and titanium are particularly interesting. On Earth, iron and titanium are solid metals. But on Kelt 9b, they're gas. They float in the air. And because iron absorbs a lot of light, the presence of gaseous iron makes the atmosphere opaque. The planet doesn't have a clear, transparent sky like Jupiter or Saturn. It has a thick metallic haze that blocks most visible light. What would the sky look like if you could somehow stand on this planet? You wouldn't survive, of course. The heat would vaporize you instantly. But if you could, the sky would glow a deep red-orange from thermal radiation. The star would dominate half the sky, a blindingly bright disk that never moves. The air around you would shimmer with heat, thick and metallic, glowing faintly from its own temperature. There would be no stars, no darkness, just endless searing light. The star's intense radiation is blowing gas off the outer layers of the planet at a rate of around 10 billion kilograms per second. That's 10,000 tons every second. To put that in perspective, Earth's entire atmosphere weighs about 5 quadrillion kilograms. Kelt 9b loses that much mass in about 15,000 years. It sounds catastrophic, but Kelt 9b is huge. It's 1.34 times the radius of Jupiter and 2.88 times as massive. Even losing 10 billion kilograms per second, it would take hundreds of millions of years to evaporate completely. But it's still happening. The planet is actively disintegrating its outer shell, peeling away layer by layer, streaming off into space in a comet-like tail. Observations using the HARPS North spectrograph in 2018 detected this escaping gas directly. The team saw absorption lines from iron and other metals extending far beyond the planet's normal radius, forming a vast cloud of vaporized material trailing behind the planet in its orbit. It's like watching a planet bleed. At some point billions of years from now, Kelt 9b will either fall into its star or shrink down to a dense, lifeless core. What we're seeing now is a snapshot of a dying world caught in the final stages of its existence. But there's something puzzling about Kelt 9b. It's not as inflated as you'd expect. Given how hot it is, you'd think the atmosphere would balloon outward like HAT P67b, but it doesn't. The radius is only 1.34 times Jupiter's, even though the temperature is twice as high as HAT P67b's. The reason is mass. Kelt 9b weighs 2.88 times as much as Jupiter, so its gravity is much stronger. That gravity pulls the atmosphere inward, compressing it despite the heat. The result is a planet that's extremely hot, but not extremely large. This is the first hint of something we'll see again and again. Once a planet gets heavy enough, heat alone isn't enough to make it grow. Gravity starts winning. The more mass you add, the more the planet compresses. And past a certain point, adding more mass actually makes the planet smaller. Kelt 9b sits near the boundary where heat and gravity are almost balanced. The heat is trying to blow the planet apart. Gravity is holding it together, and the star is slowly tearing it to pieces one atom at a time. But temperature isn't the only way to break a planet. Sometimes the violence comes from the past, from a collision so catastrophic that it flips the entire orbit backward, sending the planet spinning against the flow of everything else in its system. WASP-17b orbits its star backward. Most planets move in the same direction as their star rotates. It's a natural consequence of how solar systems form. Everything condenses out of the same swirling disk of gas spinning in the same direction like water circling a drain. The star spins. The planets orbit. Everything moves together, synchronized. But WASP-17b doesn't follow that rule. It moves in the opposite direction, looping around its star the wrong way, like a car driving against traffic on a highway. The orbital inclination is about 150 degrees relative to the star's equator. 0 degrees would mean the planet orbits in the same plane as the star's spin. 180 degrees would be perfectly retrograde, exactly backward. WASP-17b is close to that. Astronomers call this a retrograde orbit, and it's rare. Out of the thousands of exoplanets discovered so far, only a few dozen have confirmed retrograde orbits. Most of them are hot Jupiter's gas giants orbiting very close to their stars. WASP-17b is one of them, and it's among the most extreme. The planet is 1.74 times the radius of Jupiter, but only about half the mass. The density is extraordinarily low, less than a fifth the density of water. It's one of the puffiest planets we've ever found, inflated by the heat of its star into a massive, fragile shell. In some ways, it's similar to HAT P67b, a bloated gas giant barely holding itself together. But the retrograde orbit sets it apart. It tells a story of violence. Planets don't just naturally end up orbiting backward. Something violent had to happen. Something that could flip an entire orbit upside down. The leading theory is planetary scattering, a chaotic event early in the system's history where multiple large planets formed close together and their gravitational interactions sent them careening off in different directions. Frederic Russio, an astrophysicist at Northwestern University, has run thousands of computer simulations of multi-planet systems to see how often this happens. His team uses powerful supercomputers to model the gravitational dynamics of systems with 2, 3, or 4 gas giants all forming within a few astronomical units of each other. They let the simulation run for millions of years of virtual time and watch what happens. The results are striking. In systems where two or three gas giants form close together, gravitational interactions almost always destabilize the orbits. At first, the planets orbit peacefully, but tiny perturbations, small tugs from one planet on another, accumulate over time. The orbits become slightly elliptical, the ellipses get more pronounced, eventually the orbits cross and the planets have a close encounter. When two Jupiter-sized planets pass within a few million kilometers of each other, their mutual gravity flings them in new directions. One planet might get ejected from the system, entirely sent flying off into interstellar space at tens of kilometers per second. Another might crash into the star. And sometimes one planet gets flung into a highly inclined or even retrograde orbit, its trajectory completely reversed by the encounter. The process is violent. Imagine two billiard balls colliding on a pool table. One of them ricochets off at a wild angle, spinning in a way it wasn't before. Now, scale that up to planets the size of Jupiter moving at tens of kilometers per second, and the collisions aren't physical impacts, the planets never actually touch, but gravitational slingshots that can flip an entire orbit upside down in a matter of hours or days. Russio's simulations show that retrograde orbits are a natural outcome of planetary scattering. About 10 to 20% of hot Jupiters in multi-planet systems end up on retrograde orbits. The rest are ejected, destroyed, or left in highly elliptical but not retrograde orbits. The statistics match what we observe. Roughly 10% of hot Jupiters have retrograde or nearly retrograde orbits consistent with a history of violent scattering. Another possibility is the Kozai mechanism, named after the Japanese astronomer Yoshihide Kozai, who first described it in 1962. The idea is that a third object, maybe another planet farther out or a distant companion star, tugs on the inner planet's orbit over millions of years, gradually tilting it until it flips completely backward. The Kozai mechanism is subtle. It doesn't involve close encounters or violent collisions. Instead, it's a slow, steady perturbation. The third object's gravity causes the inner planet's orbit to oscillate, swinging between circular and elliptical, and between low inclination and high inclination. Over time, the oscillations can grow large enough to flip the orbit into retrograde. The process takes millions of years. It's not dramatic, it's not fast, but it's effective. And unlike planetary scattering, which requires multiple giant planets in the same system, the Kozai mechanism only requires one inner planet and one distant perturber. It's a more gentle way to produce a retrograde orbit, though it's harder to confirm observationally because you need to detect the distant third object, which is often too faint or too far away to see. Either way, WASP-17b was violently rearranged, and that violence might be why it's so inflated. A retrograde orbit creates extra tidal stress. The planet is moving one way while the star is spinning another, so the gravitational pull between them isn't smooth. The star's tidal bulge is always slightly out of alignment with the planet, and the misalignment creates friction. It's like trying to spin a basketball on your finger, but the ball is rotating in the opposite direction. You have to work against the motion, and that work generates heat. That internal heat, combined with the external heat from the star's radiation, puffs the planet up even more than it would be otherwise. David Anderson, an astronomer at the University of Warwick who has studied WASP-17-b extensively, has pointed out that the planet's low density is hard to explain without some kind of extra heating source. Radiation from the star alone isn't enough. You need tidal heating or ohmic heating or both. The retrograde orbit might be the key. The planet orbits its star once every 3.7 days at a distance of about 7 million kilometers. The star is slightly cooler than the Sun, a G-type star, similar to our own, but WASP-17b is so close that the temperature on the day side still climbs to around 1500 degrees Celsius. Not as extreme as Kelt 9b, but still hot enough to melt, lead hot enough to vaporize sulfur and phosphorus, hot enough to make the atmosphere glow faintly in infrared light. In 2023, the James Webb Space Telescope observed WASP-17b and made a discovery that stunned the astronomy community. The atmosphere contains clouds made of quartz. Not water clouds, not ammonia clouds, not methane clouds, quartz. Silicon dioxide crystals, the same material that makes up sand and glass on Earth, condensed into tiny particles floating high in the atmosphere. Nicole Lewis, an astronomer at Cornell, who led the observation, described it as one of the strangest atmospheric compositions ever detected. Quartz forms when silicon and oxygen combine at high temperatures and then cool slightly, allowing the molecules to condense into solid crystals. On Earth, this happens in volcanic environments or deep underground, where temperatures are high but not high enough to keep silicon and oxygen as separate gases. On WASP-17b, the temperature and pressure at certain altitudes are just right for this to happen. Silicon and oxygen, common elements in any rocky planet or gas giant with a rocky core, are vaporized in the deep atmosphere where temperatures are hottest. The gas rises, cools, as it ascends, and at around 1500 degrees Celsius, the silicon and oxygen combine into silicon dioxide molecules. Those molecules stick together, forming microscopic grains of quartz that drift through the upper atmosphere. The result is a haze of quartz dust suspended in the air, glittering faintly in the starlight. The particles are tiny, probably only a few microns across, smaller than grains of sand, but there are trillions of them, forming a thin veil that stretches across the planet's sky. The effect would be similar to standing in a desert on Earth during a dust storm, except the dust is made of glass and the air is hot enough to ignite paper. No other planet has been confirmed to have quartz clouds. WASP-17b is the first. And it's a reminder that these alien worlds don't just follow the rules we're used to. They invent new ones. On Earth, quartz is a common mineral found in beaches and mountains used to make glass and electronics. On WASP-17b, it's floating in the sky. The quartz clouds might also help explain the planet's strange thermal properties. Quartz is highly reflective. It bounces light back into space rather than absorbing it. That means the planet might be slightly cooler than it would be otherwise, which could affect how much the atmosphere inflates. But the effect is small, and it doesn't fully account for the planet's extreme puffiness. There's still something else going on, some additional source of heat that's keeping the planet inflated beyond what radiation alone can explain. The planet won't stay this inflated forever. Like HAT-P67b and KELT-9b, WASP-17b is losing atmosphere. The star's radiation is stripping gas away at a rate of around 100 million kilograms per second. Not as fast as KELT-9b, but still significant. Over hundreds of millions of years, the outer layers will thin. The planet will shrink. The quartz clouds will dissipate as the atmosphere cools and contracts. What's left will be smaller, denser, and quieter. Sarah Seeger, a planetary scientist at MIT, has argued that super-puffed planets like WASP-17b are essentially living fossils. They're remnants of an earlier era in the planet's history, when it was farther from the star and cooler. Something, maybe planetary migration driven by interactions with the protoplanetary disk, maybe gravitational scattering from another planet pushed it inward to its current position. Now it's stuck in an environment it wasn't designed for, slowly being destroyed by the star's heat. The retrograde orbit supports this idea. If the planet originally formed farther out and was then scattered inward by a gravitational encounter, the scattering event could easily have flipped the orbit backward. The planet we see today is a survivor of that encounter, scarred and transformed, carrying the evidence of its violent past in the direction of its motion. For now, WASP-17b is a monument to chaos, a backward planet with glass clouds bloated by heat and scarred by some ancient catastrophe we can only reconstruct from the orbit it left behind. All the planets we've talked about so far are inflated, puffed up by heat into sizes larger than they should be. But there's a completely different kind of giant out there. One that's not inflated at all. One that's so massive it barely fits the definition of a planet anymore. And adding more weight to it doesn't make it bigger, it makes it smaller. Rox's 42b weighs 9 times as much as Jupiter, but it's only 1.24 times wider. Stop and think about that for a second. HAT-P67b is twice Jupiter's size, but weighs a third as much. Rox 42b is 26 times heavier than HAT-P67b, but smaller in radius. This is the first time we see the paradox clearly. Adding mass doesn't make a planet bigger. Past a certain point, it makes it smaller. The reason is gravity. When a planet is light, gravity is weak, so the gas spreads out. When a planet is heavy, gravity is strong, so the gas gets crushed inward. At 9 Jupiter masses, the gravity is so intense that even though there's 9 times as much material, it's compressed into a ball only slightly larger than Jupiter itself. The density is much higher than any of the inflated planets we've discussed, somewhere around 4 to 5 times the density of water depending on the exact composition. That's closer to rock than gas. Deep inside Rox's 42b, the pressure is so extreme that hydrogen stops behaving like a normal gas or liquid. It enters a strange state called metallic hydrogen, where the electrons are stripped away from the atoms, and the hydrogen conducts electricity like metal. Below that, there might be a solid core of rock and iron compressed to densities higher than anything on Earth. Rox's 42b is also young, very young. The star it orbits is only about 3 million years old, and the planet formed around the same time. For comparison, Jupiter is 4.6 billion years old. Rox's 42b is still in its infancy, and because it's so young, it's still hot from the energy released during its formation. When a planet forms, gravitational potential energy is converted into heat as material collapses inward. For a massive planet like ROX's 42b, that heat is enormous. The planet glows from its own internal warmth, radiating in infrared wavelengths. The surface temperature is around 1500 degrees Celsius, even though the star isn't heating it. It's hot because it hasn't cooled down yet. Over the next few billion years, Rox's 42b will gradually lose that heat, radiating it away into space. The glow will fade, the temperature will drop. Eventually, it will become a cold, dark object no longer visible except by reflected starlight. The planet orbits incredibly far from its star, 157 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, so ROX's 42b is 157 times farther from its star than we are from ours. Pluto, at its farthest, is only about 50 astronomical units out. Rox's 42b is more than 3 times farther than Pluto. At that distance, the star is just a bright dot in the sky. There's almost no heat coming from it. The planet is essentially alone, drifting in the cold outer reaches of its system, glowing softly from its own residual warmth. Because it's so far from its star and still glowing, Rox's 42b was discovered using direct imaging. Most exoplanets are found indirectly, by watching a star dim as a planet passes in front of it, or by measuring the wobble in the star's motion caused by the planet's gravity. But Rox's 42b was photographed directly. Telescopes at the Keck Observatory in Hawaii, equipped with adaptive optics and infrared cameras, spotted the faint red glow of the planet against the black background of space. The discovery was announced in 2013, and it immediately sparked debate. Is Rox's 42b even a planet? At 9 Jupiter masses, it's getting close to the boundary between planets and brown dwarfs. Brown dwarfs are often called failed stars, objects that are too small to sustain hydrogen fusion like a real star, but too big to be considered planets. The official dividing line set by the International Astronomical Union is 13 Jupiter masses. Below that, you're a planet. Above that, you're a brown dwarf. The reason for the cutoff is deuterium fusion. Deuterium is a heavier isotope of hydrogen, and it burns at a much lower temperature than regular hydrogen. Once an object reaches about 13 Jupiter masses, the core gets hot enough and dense enough to ignite deuterium fusion. At that point, the object is producing energy through nuclear reactions, not just leftover heat from formation. Rox's 42b is 9 Jupiter masses. Still a planet technically, but it's approaching the edge. Michael Liu, an astronomer at the University of Hawaii who was part of the discovery team, has pointed out that the distinction between massive planets and low-mass brown dwarfs is somewhat arbitrary. The physics is continuous. There's no sharp transition. An object at 12 Jupiter masses and an object at 14 Jupiter masses are fundamentally very similar. One just happens to have enough mass to burn deuterium, and the other doesn't. But the classification matters for other reasons. How an object forms tells you something about what it is. Planets form in a disk of gas and dust around a star building up from small solid cores that accrete gas. Brown dwarfs form the same way stars do, collapsing directly from a cloud of gas without needing a solid core first. Rox's 42b probably formed like a planet. It's orbiting a star. It's in the outer part of the system where planets usually form, and its mass is consistent with core accretion models. But some researchers have argued that it might have formed like a brown dwarf through gravitational collapse of a fragment of the protostellar disk. The jury is still out. What's clear is that Rox's 42b represents a different regime of planetary physics. It's not inflated by heat. It's not evaporating into space. It's massive enough that gravity dominates everything else. And it shows us what happens when you keep adding mass to a gas giant. At 1 or 2 Jupiter masses, the planet is near its maximum size. The gas is as spread out as it's going to get. Add more mass and gravity starts compressing the gas inward. At 5 Jupiter masses, the planet is about the same size as Jupiter, maybe even slightly smaller. At 10 Jupiter masses, it's noticeably smaller. At 13 Jupiter masses, right at the brown dwarf boundary, it's only about 90% of Jupiter's radius, and it keeps shrinking. At 30 Jupiter masses, the radius is about 80% of Jupiter's. At 50 Jupiter masses, it's down to 70%. The more mass you add, the smaller the object gets, until eventually it starts resembling a white dwarf star, an incredibly dense ball of matter held up by quantum mechanical pressure. Rox's 42b is on that trajectory. It's heavy enough that gravity has started winning over thermal pressure, and it's a preview of what we'll see if we go even heavier. That 13 Jupiter mass limit the boundary where deuterium fusion ignites and planets become brown dwarfs is the first wall. The first absolute barrier that no planet can cross. But there's a second wall too, one that has nothing to do with fusion or nuclear reactions, and everything to do with a bizarre quantum force that kicks in when you try to compress matter past a certain point. The universe has rules, and one of those rules is this: if an object weighs more than 13 times the mass of Jupiter, it's not a planet anymore. It's a brown dwarf. The reason is deuterium. Deuterium is an isotope of hydrogen. It has 1 proton and 1 neutron in its nucleus, instead of just 1 proton like normal hydrogen. It's rare. Only about 15 out of every 100,000 hydrogen atoms in the universe are deuterium. But it's important because deuterium fuses at much lower temperatures than regular hydrogen. Normal hydrogen fusion, the kind that powers stars like the Sun, requires core temperatures of around 10 million degrees Celsius. That takes a lot of mass. You need at least 80 Jupiter masses to compress the core enough to reach that temperature. Anything smaller, and the core stays too cool. Fusion never starts. The object never becomes a true star. But deuterium fusion is different. It ignites at around 1 million degrees Celsius. That's 10 times cooler. And you only need about 13 Jupiter masses to reach that temperature in the core. So, when an object hits 13 Jupiter masses, the core heats up from gravitational compression. Deuterium starts fusing, and energy begins pouring out from nuclear reactions. The object is no longer a cold ball of gas held together only by gravity. It's generating its own light and heat. It's crossed the line into being a brown dwarf. The distinction was formalized by the International Astronomical Union in 2003 after years of debate. Before that, there was no agreed-upon definition. Some researchers used mass, some used formation mechanism, some used whether the object emitted its own light. Arguments broke out at conferences. Papers were written attacking and defending different definitions. The field was a mess. The IAU settled on the 13 Jupiter mass threshold because it's based on clear physics. Deuterium fusion either happens or it doesn't. There's no ambiguity. You can measure it. You can see the difference in the object's spectrum when fusion turns on. The object starts emitting more light. The surface temperature increases. The internal structure changes. It's a clean dividing line. Jibor Basri, an astronomer at UC Berkeley who was part of the working group that defined the boundary, has described it as one of the few truly clean dividing lines in astrophysics. Most categories, like the difference between a large rocky planet and a small gas giant, or between a planet and a dwarf planet, are fuzzy and debatable. People argue about them, Pluto is still a sore subject in some circles, but the deuterium limit is sharp. Below 13 Jupiter masses, deuterium doesn't fuse. Above 13 Jupiter masses, it does. End of discussion. Brown dwarfs are sometimes called failed stars because they're not quite massive enough to fuse regular hydrogen. They burn deuterium for a while, maybe 10 to 100 million years, depending on how much deuterium they started with, and then they run out of fuel. The fusion stops, the brown dwarf cools and fades glowing dimly in infrared for billions of years as it slowly radiates away its leftover heat. The cooling process is predictable. Young brown dwarfs are hot surface temperatures of 1000 to 2000 degrees Celsius. They glow red, visible in infrared telescopes. As they age, they cool. After a few 100 million years, the surface temperature drops to a few 100 degrees. After a billion years, they're cooler than boiling water. After 10 billion years, they might be room temperature or colder invisible, except in very long infrared wavelengths. Eventually, brown dwarfs cool so much that they stop glowing altogether. They become black dwarfs, cold and dark, drifting invisibly through space. The universe isn't old enough yet for any black dwarfs to exist. Even the oldest brown dwarfs are still faintly warm, but in trillions of years, the galaxy will be filled with them. Dead stars that never quite became stars. Real stars, on the other hand, fuse regular hydrogen. They burn steadily for billions or even trillions of years, depending on their mass. The Sun will keep fusing hydrogen for another 5 billion years. Small red dwarfs, the most common type of star, can last for 10 trillion years or more, far longer than the current age of the universe. So the spectrum looks like this. Below 13, Jupiter masses planet. Between 13 and 80, Jupiter masses brown dwarf. Above 80, Jupiter masses star. 3 categories, 2 boundaries, all defined by nuclear physics. The first brown dwarf was discovered in 1995, almost simultaneously with the first exoplanet. Gliese 229b, orbiting a red dwarf star about 19 light-years from Earth, was confirmed to have a mass between 20 and 50 Jupiter masses. It was too light to be a star, too heavy to be a planet. It fit the brown dwarf category perfectly. The discovery paper published in Nature called it a substellar companion because the term brown dwarf wasn't yet official. Since then, thousands of brown dwarfs have been discovered, both orbiting stars and floating freely in space. Some of them are incredibly cool. Y0855-0714, discovered by NASA's Wide Field Infrared Survey Explorer satellite, is one of the coldest brown dwarfs known. Its surface temperature is around -23 degrees Celsius, colder than Antarctica, colder than the winter surface of Mars. It's so cool that it might have water clouds in its atmosphere, just like Earth. Water clouds on a brown dwarf sound strange, but they're possible. At temperatures below 0 Celsius, water vapor can condense into ice crystals, forming clouds. The atmosphere would look like a perpetual blizzard, except the ground below the clouds is still gas compressed by gravity into something like a liquid. You couldn't land on it. You'd just sink deeper and deeper until the pressure crushed you. Other brown dwarfs are hot. Young brown dwarfs, still glowing from formation, can have surface temperatures of 2000 degrees Celsius or more, hotter than molten lava. They look like dim red stars visible only in infrared light. Their atmospheres are filled with vaporized metals, sodium, potassium, iron, creating complex weather patterns with clouds, storms, and temperature variations. And all of them share one thing in common. They're shrinking. As a brown dwarf ages and cools, it contracts. The radius gets smaller. At 100 million years old, a brown dwarf might be about the size of Jupiter. At 1 billion years old, it's noticeably smaller. At 10 billion years old, it's even more compact. The mass doesn't change, brown dwarfs don't lose significant amounts of material, but the radius keeps decreasing as the object cools and the gas contracts. This is the same process we see in massive planets. Rox's 42b, at 9 Jupiter masses, is already shrinking as it cools. Over the next few billion years, it will contract to perhaps 90% of its current size. If it were 13 Jupiter masses, instead of 9, it would be doing the same thing, just with deuterium fusion, adding a bit of extra heat that slows the contraction. The 13 mass limit is the first wall. If you want to build the most massive planet possible, you can go up to 12.9 Jupiter masses. Add any more, and it stops being a planet. It becomes something else, a brown dwarf. An object that, for a brief time, generates its own energy through nuclear reactions before fading into cold obscurity. But even before you hit that wall, something strange starts happening. Something that limits how big a planet can get, not how heavy. The effect is subtle at first. At 2 or 3 Jupiter masses, the planet is only slightly smaller than Jupiter itself. But as you keep adding mass, the compression becomes more noticeable. At 5 Jupiter masses, the planet is about the same size as Jupiter, or maybe even a bit smaller. At 9 Jupiter masses like Rox's 42b, the planet is noticeably more compact. At 13 Jupiter masses, it's about 90% of Jupiter's radius, even though it weighs 13 times as much. The trend continues as you go heavier. At 30 Jupiter masses, the radius is about 80% of Jupiter's. At 50 Jupiter masses, it's even smaller. The reason is a quantum mechanical effect called electron degeneracy pressure, and it's the foundation of the second wall. This wall is stranger than the first. It doesn't care about fusion or nuclear reactions. It's built into the fabric of matter itself, and it means that no matter how much mass you add, no matter how hot you make a planet, you can never make it wider than about twice the size of Jupiter. Here's the paradox. If you take Jupiter and add more gas to it, you'd expect it to get bigger. More material, more volume, larger planet. And at first, that's true. If you add a little bit of mass, say 10 or 20% more, the planet does expand slightly. The extra gas spreads out and the radius increases. But if you keep adding mass, something strange happens. The planet stops growing, and then around 1 to 2 Jupiter masses, it actually starts shrinking. The more mass you add, the smaller it gets. At 5 Jupiter masses, the planet is roughly the same size as Jupiter, or maybe a bit smaller. At 10 Jupiter masses, it's noticeably smaller. At 13 Jupiter masses, right at the brown dwarf boundary, it's only about 90% of Jupiter's radius. The trend continues. At 30 Jupiter masses, the radius is down to about 80% of Jupiter's. At 50 Jupiter masses, it's even more compact. This seems impossible. How can adding more material make something smaller? The answer is gravity. As you add mass, gravity gets stronger. Stronger gravity compresses the gas more tightly. And past a certain point, the compression wins over the expansion. The planet gets denser instead of bigger. But there's a limit to how much you can compress matter, and that limit comes from quantum mechanics. Inside a gas giant, the hydrogen atoms are packed close together. At the pressures deep inside Jupiter, millions of times Earth's atmospheric pressure, the atoms are squeezed so tightly that the electrons surrounding them start to overlap. Electrons are quantum particles, and they obey something called the Pauli exclusion principle, discovered by Wolfgang Pauli in 1925. The principle says that no two electrons can be in the same quantum state at the same time. When you try to squeeze electrons closer together, they resist. They're forced into higher and higher energy states because the lower energy states are already occupied. The act of forcing them into those higher states creates an outward pressure. This pressure has nothing to do with temperature. It's purely a quantum mechanical effect arising from the fundamental properties of electrons. This is called electron degeneracy pressure, and at very high densities, it becomes strong enough to hold up the weight of an entire planet. The concept was first applied to stars by Subrahmanyan Chandrasekhar, an Indian astrophysicist who was only 20 years old when he made the discovery. In 1930, while traveling by ship from India to England to begin his graduate studies at Cambridge, Chandrasekhar worked out the physics of what happens when a star runs out of fuel and collapses. He realized that electron degeneracy pressure would hold the star up, but only if the mass was below a certain limit. Above that limit, which turned out to be about 1.4 times the mass of the Sun, the star would collapse further, eventually forming a neutron star or black hole. That limit is now called the Chandrasekhar limit, and it's one of the most important results in astrophysics. Chandrasekhar won the Nobel Prize in Physics in 1983 for this work, more than 50 years after he first derived it. The same physics applies to planets. Inside a gas giant, as you add more mass, the pressure increases. and eventually electron degeneracy kicks in. The electrons can't be compressed any further without creating enormous pressure. That pressure pushes outward, counteracting gravity. The result is a strange equilibrium. Gravity is pulling everything inward. Degeneracy pressure is pushing outward. The two forces balance, and the planet reaches a stable size. Add more mass, and gravity increases, but so does degeneracy pressure. The planet doesn't expand, it just gets denser. For gas giants, the effect becomes significant above a few Jupiter masses, and it means there's a maximum size a planet can ever reach, regardless of how much mass you pile on or how hot you make it. That maximum size is around 2.1 to 2.2 Jupiter radii, about 300,000 kilometers in diameter. HAT P67b, the widest planet we've found, is 2.04 Jupiter radii. It's almost exactly at the theoretical limit. And it's only that big because it's extremely hot and extremely light. The heat inflates the outer layers, and the low mass means gravity is too weak to pull them back down. But even with those perfect conditions, it can't get much bigger. If you tried to inflate it further, the outer layers would just blow away into space. The planet would disintegrate. If you tried to make a planet bigger by adding more mass, gravity would crush it smaller. If you tried to make it bigger by heating it up, more the atmosphere would evaporate. There's no way around the limit. Tristan Guillot, a planetary scientist at the Côte d'Azur Observatory in France, has spent years modeling the interiors of gas giants and brown dwarfs. His models show that the 2.2 Jupiter radius limit is a hard ceiling. No stable planet can exceed it. Even under the most extreme conditions, imaginable orbiting right at the edge of its star, heated to thousands of degrees, made of the lightest possible materials, a planet can't get wider than about twice Jupiter's size without falling apart. This is the second wall, and unlike the first wall, which is about mass, this one is about size. It doesn't matter if you're a light puffy planet like HAT P67b, or a massive compressed planet like Rox's 42b. You can't break through. The same limit applies to brown dwarfs. Even though brown dwarfs can be 50 or 60 Jupiter masses, they're smaller than Jupiter. A 50 Jupiter mass brown dwarf has a radius of about 70 to 80% of Jupiter's radius. It's incredibly dense, held up entirely by electron degeneracy pressure, and it can't expand no matter how much heat it generates from deuterium fusion. At even higher masses, around 80 to 100 Jupiter masses, objects transition from brown dwarfs to true stars, and they start fusing regular hydrogen. But even then, they don't get much bigger. The smallest red dwarf stars are only about 10 to 15% larger than Jupiter, despite being 100 times more massive. The extra mass just makes them denser. The pattern is clear. Once an object reaches a certain size, adding more mass doesn't make it grow. It makes it shrink, and the maximum size is set by a fundamental quantum limit. Jupiter is about 70% of the maximum size. Saturn is about 60%. HAT P67b is 97%. No planet will ever be bigger. So, we have two walls, 13 Jupiter masses where planets become brown dwarfs, and 2.2 Jupiter radii where physics simply won't allow a planet to grow any larger. Every planet in the universe is trapped between these limits. And the planets that push closest to the walls, they're all dying. Every planet we've talked about, HAT P67b, Kelt 9b, WASP 17b, Tres 4b, Rox's 42b, they're all temporary. None of them will last in their current state. The inflated ones are evaporating. HAT P67b is losing around 10 million kilograms of atmosphere every second. That sounds like a lot, but the planet is so massive that it would take hundreds of millions of years to lose even 10% of its mass. Still, the process is happening. Every second, high-energy photons from the star slam into the upper atmosphere, knocking atoms loose and sending them flying off into space. The atmosphere thins. The planet shrinks. Eventually, what's left will be a smaller, denser core, no longer the widest planet in the known universe. Kelt 9b is losing gas even faster, 10 billion kilograms per second. The star's radiation is so intense that it's not just stripping the atmosphere, it's vaporizing it. Iron, titanium, sodium, magnesium, all of them floating around as loose atoms being blown away into space like smoke from a fire. Over time, the outer layers will peel away completely. What remains might be a dense, rocky core, or perhaps nothing at all consumed by the star it orbits. WASP-17b, with its quartz clouds and retrograde orbit, is also evaporating, 100 million kilograms per second. The glass-like haze that makes it so unique will eventually disperse. The planet will contract. The backward orbit might survive, that's determined by the planet's angular momentum, which doesn't change, but the bloated, fragile shell we see today won't. The mechanism driving all of this is atmospheric escape. It's not a gentle process. High-energy ultraviolet and X-ray photons from the star hit molecules in the upper atmosphere and ionize them, stripping away electrons. The ionized atoms become charged particles, and they're accelerated by the planet's magnetic field, or simply heated to such high velocities that they exceed the escape velocity and fly off into space. For planets orbiting close to their stars, this process is fast. The closer the planet, the more intense the radiation. WASP-12b, which orbits at just 3.4 million kilometers from its star, is being destroyed so quickly that astronomers have predicted it will only survive another 10 million years before it either falls into the star or evaporates completely. WASP-12b is an extreme case, but it's not unique. Many hot Jupiters are in the process of spiraling inward toward their stars. The mechanism is tidal decay. The planet raises tides on the star, just like the moon raises tides on Earth. Those tides create bulges in the star's surface, and the bulges lag slightly behind the planet's orbit because the star rotates more slowly than the planet orbits. The gravitational pull between the bulge and the planet creates a drag force that saps energy from the orbit. Over millions of years, the orbit shrinks and the planet moves closer to the star. Closer means hotter. Hotter means more evaporation. More evaporation means less mass. Less mass means a weaker gravitational hold on the orbit. The process accelerates. It's a death spiral, and there's no way out. Joshua Wynne, the Princeton astronomer who has studied tidal decay extensively, has described hot Jupiters as being on borrowed time. Most of them won't survive for more than a few 100 million years in their current orbits. Some will fall into their stars. Others will evaporate down to rocky cores. A few might migrate outward, pushed by interactions with other planets or the protoplanetary disk, but those are rare. The super-puffed planets are especially vulnerable. They only exist because they're being constantly heated. Take away the heating and they collapse. HAT P67b, TRES4b, WASP-79b. All of them are inflated by the heat of their stars, and they'll only stay inflated as long as that heat continues. But the heat is also killing them. It's a paradox. The same force that makes them record holders is the force that ensures they won't hold those records for long. Even planets that aren't being roasted are temporary in a different sense. Rox's 42b is young, only 3 million years old. It's still glowing from the heat of formation. Over the next few billion years, it will cool. The surface temperature will drop from 1500 degrees Celsius to just a few hundred degrees, then to near absolute zero. The glow will fade. The planet will become dark and cold, drifting silently through the outer reaches of its system, invisible except for the faint starlight it reflects. It's not dying in the same way HAT P67b is dying. It's not evaporating or spiraling into its star, but it's still changing. The planet we see today, a glowing massive giant, is not the planet that will exist a billion years from now. The universe doesn't allow permanent giants. Planets exist in a state of flux. They form, they evolve, they change. The stable ones like Jupiter and Saturn sit in environments where the forces acting on them are balanced. They're far enough from the sun that radiation isn't a threat. They're massive enough that evaporation is negligible. Their orbits are stable, locked in place by the gravitational architecture of the solar system. But the extreme planets, the record holders, the ones pushing against the two walls, they're all in unstable environments. They're either too close to their stars, or too young, or caught in strange orbits that subject them to forces they can't withstand indefinitely. Sarah Seeger has pointed out that the planets we find tell us as much about the limits of planet formation as they do about the planets themselves. We find super-puffed planets, because they're big and easy to detect. We find hot Jupiters because they orbit close to their stars and create large, frequent transits. But we're seeing them in a brief window of their existence, a snapshot in time. In a few 100 million years, the population of known exoplanets will look different. The super-puffed planets will have shrunk. The hottest planets will have evaporated or fallen into their stars. New planets, currently undetectable because they're smaller or farther from their stars, will take their place in the rankings. But the two walls will remain: 13 Jupiter masses, 2.2 Jupiter radii. Those are the limits written into the physics of matter and energy, and no planet in this universe or any other will ever cross them. The 10 largest planets we've found: Hat P, 67b at the top, Wasp 17b, with its quartz clouds, Kelt 9b, burning hotter than stars, Tress 4b, inflated like a balloon, Wasp 79b with its strange chemistry, and half a dozen others we haven't named. They're all pushing against those walls, and every single one of them is paying the price. They're evaporating, shrinking, spiraling inward, cooling down, changing into something else. None of them will last forever. Most of them won't even last a billion years. The largest planets are the most fragile. The hottest are dying the fastest. And the ones that break the rules, the backward orbits, the quartz clouds, the super-puffed atmospheres, they only exist because something violent happened or because they're sitting in conditions so extreme they can't endure. Jupiter and Saturn, the two kings we started with, are ordinary by comparison. They're not the biggest. They're not the hottest. They don't have retrograde orbits or evaporating atmospheres, but they're stable. They've been here for 4.5 billion years, and they'll be here for billions more. And maybe that's the real lesson. In a universe full of extremes, the giants that survive aren't the ones pushing the limits. They're the ones that know when to stop growing. The walls are there for a reason. They're not arbitrary. They're built into the fundamental physics of matter: the temperature at which deuterium fuses, the pressure at which electrons resist compression, the speed at which hot gas escapes into space. No planet will ever cross those walls. Not in this solar system, not in any other. The record holders we've found are already at the edge. And beyond the edge, there's nothing but collapse, evaporation, and transformation into something that's no longer a planet at all. The universe sets the rules, and the planets, no matter how massive or how strange, have no choice but to follow them.